This is the first video in a series that aims to explain quantum physics in a more intuitive way. Before we talk about anything quantum, we need to lay some foundations, and those foundations start with Ludwig Boltzmann. So let's get right into it. Picture a mass on a spring. The dashed line represents the equilibrium point, and currently the system has no energy and it's at rest. But let's give the system some energy and watch what happens. The system begins to oscillate back and forth. Here we're measuring two things. The first is x, the displacement. This shows how far forward or how far back the mass is from the equilibrium point at any given point in time. The second is p, the momentum of the mass. These values constantly change with time. The momentum reaches a maximum right as it passes through the equilibrium point, where the displacement is zero. Similarly, the displacement reaches a maximum right as it reaches the turnaround point, where the momentum is zero. These two values seem to chase one another. Let's take a look at what we see when we plot the displacement against time and the momentum against time on a graph. We get two sinusoidal waves that are slightly out of phase with each other. Here, you can also see how the displacement is maximum when the momentum is zero. And here you can see how the momentum is maximum when the displacement is zero. Notice how if you took any point in time, there's always a value of x and a value of p. So let's take a few values of time and take the corresponding x and p values. Just from these values alone, we can learn a lot about the state of a system. When the displacement is maximum and the momentum is zero, we know the mass must be at a turnaround point. And when the momentum is maximum and the displacement is zero, we know the mass must be travelling through the equilibrium position. The time we took the values isn't really important anymore. All the information we want about the phase of the system is encoded in these two variables. And if we treat these pair of variables like coordinates, instead of just values, we can create interesting ways to visualize it. Let's make a graph, with the x-axis as the displacement and the y-axis as the momentum. And let's plot the values on here. This graph is what we would call a phase space diagram, because it tells you where the system is in phase space. As you can see, it traces an ellipse. The reason it's an ellipse is because the spring in this example isn't losing any energy, it's just oscillating. This energy conservation is actually encoded into this diagram. The total energy of any system is the kinetic energy plus its potential energy. This is called the Hamiltonian. We can represent the kinetic energy in terms of momentum here, p squared over 2m, and the potential energy in terms of the displacement here, half kx squared. If you want to dig deeper into why the kinetic energy ends up being related to the momentum in this way, that comes out of Newtonian mechanics. And if you're curious why the potential energy of a spring goes like 1/2 kx squared, that comes out of Hooke's law. But k and m are just constants in this equation for a specific mass spring system. K is the stiffness of the spring and m is the mass on the spring. So now if we plug the live values of p and x from this graph into this equation, we can find the energy at any point. As you can see, the energy is constant. No matter where the system is in phase space, it has the same amount of energy. If there was less energy in the system, the ellipse would be smaller. Each of these concentric rings represents a different total energy the spring system can have. A large amplitude oscillation lies in a large spring, while a small amplitude oscillation lies in a smaller one. Let's imagine our mass spring system is now interacting with its environment. It's connected to a heat bath, something it can exchange energy with. If it transfers a certain amount of its energy to the heat bath, it ends up in a smaller energy state. This gives us a more practical picture of how real systems behave. They interact with their environment, exchange energy, and move through different regions of phase space corresponding to different energy levels. Boltzmann comes in here and he asks the following question. If you were to randomly observe a spring like this in the real world, what is the probability that it exists in a certain point in phase space? We can represent those probabilities visually using a heat map over phase space. This represents how likely it is that a spring exists at a given point in phase space. The lower the energy level, the more likely it is, and Boltzmann created an equation to explain this probability distribution. The left side of this equation, P xp, is just saying the probability for a given point of displacement x and momentum p in phase space. We'll worry about the right side of the equation later, but for now, just consider the left a function. It takes in two numbers, x and p, for any position in phase space, and outputs a number that tells you how likely that region of phase space is to be occupied. But Boltzmann didn't just pull this equation out of thin air. Let's take a look at how he got there. By the mid-1800s, physics seemed almost complete. Most of the known world could be explained using Newtonian mechanics. Force, mass, acceleration. If you knew the forces acting on something, you could predict how it would move. This framework worked extraordinarily well, but as the Industrial Revolution took hold and steam engines began powering the world, physics ran into something new. They weren't just studying motion anymore, they were studying heat. From experiments, a new set of patterns emerged. They knew that hot objects cool down, and they knew that energy spreads out. These patterns were extremely reliable, but there was a problem. None of this behaviour could be grounded in Newton's laws. The equations of motions don't know what hot or cold mean. They don't know whether energy is concentrated or spread out, and yet the real world clearly does. So physicists were left with a deep question. How can we ground these observed laws of thermodynamics in Newtonian mechanics? Enter Boltzmann. In 1877, an Austrian physicist named Ludwig Boltzmann approached the problem from a completely different angle. Instead of asking how thermodynamic systems move, he asked how many ways they can exist. To do this, he used a thought experiment. You have a spring, and this spring exists within the universe. Let's assume there's a fixed amount of energy that exists in the universe. That total energy is shared between the spring and everything else in the universe. If the spring gains energy, the rest of the universe must lose the same amount. If the spring loses energy, the rest of the universe gains it. But what does this energy split usually look like? A split where most of the energy is in the spring seems intuitively wrong. Of course the spring won't have more energy than the rest of the universe. But before Boltzmann, there was no physical law to ground this other than common sense. Boltzmann's idea was to use counting to give us more information about how this energy is likely split in systems like this. He decided to count how many microscopic states correspond to each possible way of splitting the energy. But what is a microscopic state? Let's return to the phase space picture. At a microscopic level, the spring can exist in many different configurations, different positions and momenta. For a given energy, all of these configurations lie on the same orbit in phase space. We call each of these possibilities a microstate, and we can refer to the number of possible microstates for an energy E as omega. We want to think about how the number of microstates for this spring system changes as the energy changes. It seems intuitive that the more energy is in the spring, the bigger the circle, so the larger the number of possible microstates, right? But that isn't quite the case. To count them properly, we need to think in terms of small regions rather than exact points. The number of microstates is not correlated to the circumference of this ellipse, but to the area that is covered by it. The thickness of the ellipse matters too. Let's take the area of this ellipse at a large energy and reshape it into a straight line. Now there's something I haven't been telling you about this ellipse, and now is the right time to introduce it. The thickness of the ellipse is bigger at a smaller energy than it is at a higher energy. We will get into why later, but for now, this is a more accurate representation of what an ellipse would look like at a smaller energy. Let's take the area covered by this lower energy ellipse and reshape it into a line too. We can see that the total area covered by both a large energy and a small energy is the exact same. This is called the phase area, and the number of microstates for a given energy level is proportional to that energy level's phase area. As we demonstrate here, For our mass spring system, the phase area doesn't change, no matter how much energy is in the system. Therefore, the number of microstates doesn't change either. There are the same amount of microstates in the system if there's a tiny bit of energy as if there's a gigantic amount of energy. The number of microstates at any energy level is constant. So why does the thickness of the band decrease as the energy grows? Well, let's take two energy levels, E1 and E2. The thickness of the band represents how much X and P can change before the energy changes by a fixed small amount. Since the equation shows the energy depends on the squared values of X and P, if you want to keep E within a certain range, the tolerance for X and P decreases as E increases. Since energy is continuous, the measurements aren't exact. Let's say for energy 1, we want to find the number of microstates that correlate to an energy level of 0.03. We can allow a tolerance and include all microstates that correlate to an energy between 0.025 and 0.035. This will allow a minimum P and X value in the inner layer of this band, at say 0.18 and 0.11. That returns a lower energy bound and is still a valid microstate. It will also allow a maximum P and X value at the outer layer of this band, at say 0.23 and 0.14. That returns the upper energy bound and is also a valid microstate. Then for energy level 2, we may say that we want to find the number of microstates that correlate to an energy level of 0.46. We allow the same tolerance and include all microstates that correlate to an energy of 0.455 and 0.465. This will allow a minimum P and X value in the inner layer of this band, at say 0.82 and 0.48, and that returns the lower energy bound and is a valid microstate. And it will also allow a maximum P and X value on the outer layer of this band, at say 0.84 and 0.48. That returns the upper energy bound and is also still a valid microstate. So there is more wiggle room at lower energies on the values of momentum and position, but also a smaller range of total values. So, at low energies, the band is short but thick, and at high energies, it's long but thin. And in both cases, the total phase space area is the same. So what does this mean? For our thought experiment, with a single spring in the universe, no matter how much energy the spring has, the number of microscopic configurations available to it is the same. Whether the spring has 1 joule or 1 million joules of energy, there are the same number of ways the spring can be configured to represent that energy. Now let's consider what would happen if, instead of the 1 spring system, we had a 2 spring system. So instead of only being able to put the energy into 1 spring, there would be 2 different ways of distributing it. The total energy of the system would be fixed, and there would be any combination of distributions of that energy amongst the 2 springs. We could have a majority of the energy in 1 spring and only a small bit in the other, or vice versa, or have the energy split amongst them equally. So let's lay out the different ways we could divide the energy up in a 2 spring system. Of course, this is continuous, so we will just take samples of it as the distribution changes to make it more discrete to help us. So, for each of these different distributions, we have a number of microstates that could exist for spring 1 at this energy level E1, and a number of microstates that could exist for spring 2 at this energy level E2. Let's call them omega 1 and omega 2. For any given microstate of omega 1, omega 2 could exist in any of its microstates. So, to find the total number of possible microstates between both springs for this energy distribution in particular, we multiply them to get a square with the area omega 1 by omega 2. Earlier, we worked out that no matter how much energy is in a single spring system, the number of microstates correlating to that energy level would be the same. Therefore, as the energy distribution changes for spring 1, omega 1, the number of microstates that correlate to that energy, will remain the same. And as the energy distribution changes for spring 2, omega 2, the number of microstates that correlate to that energy, will also remain the same. So, for each energy distribution, the number of microstates for that energy distribution will be omega 1 multiplied by omega 2. A cool way to visualize it is this stack of squares. These omega values depend only on the spring parameters K and M, not on the energy, so we can treat them as constants. So, the total number of microstates available in a system with two springs is proportional to this square constant multiplied by the number of possible energy distributions. Therefore, as the total energy of the two-spring system increases, the number of possible energy distributions between the springs also increases. Since each distribution contributes the same number of microstates, the total number of microstates corresponding to that total energy increases as well. So, when we compare how the number of microstates available at a specific energy E changes as the amount of energy allocated to that system increases, for a one-spring system with 1 degree of freedom and for a two-spring system with 2 degrees of freedom, we can see that in the one-spring system it doesn't change at all, and for the two-spring system it grows linearly with energy. So what do we think it will look like for a system with 3 degrees of freedom in a three-spring system? We can use the same logic that we did for the 2D system, but just add another dimension to it. The range of potential energy distributions increases, and now each distribution has a number of omega 1 multiplied by omega 2 multiplied by omega 3 microstates, so the square turns into a 3D cube. But remember, this is just a constant, and the cube is not related to the amount of energy in the system. And what we care about here is how this number changes with increasing amounts of energy. And since increasing the energy doesn't change the cube, that's not so important to us. What really changes with increasing energy is how many different splits of energy are available. This tells us what the cube is multiplied by to get to the total number of microstates. To better understand how the number of microstates changes with energy as the degrees of freedom in the system increase, a better question would be, how does the number of possible energy distributions increase as the degrees of freedom increase? Let's look at this geometrically to understand. For one spring, there's only one way of splitting the energy. This point represents the only possible split of energy. For two springs, the number of ways it can be split can be represented as a line. Anywhere on this line will be a value of E1 and the value of E2, where E1 plus E2 is the total energy in the system. The energy split space here is proportional to E. If there were three springs, the number of possible splits can be represented as a triangle, where E1 plus E2 will leave some remainder between that and the total energy, and that remainder is the value of E3. So although E3 isn't a dimension on the triangle, it is implicit and can be worked out based off the values of E1 and E2. You can select any point in this triangle's energy split space and get a value of E1 and E2, and therefore work out the value of E3, and that will represent a unique energy distribution. Here, the energy split space is proportional to E squared. If there were four springs, we could represent the energy split space in 3 dimensions, E1, E2 and E3 on each axis. E4 is now the implicit hidden constraint. Again, selecting anywhere in this volume gives you a unique energy distribution with 4 values, E1, E2, E3 and an implicit E4. The split space here is proportional to E cubed. So we can see the pattern. As the number of degrees of freedom increase, the energy split space becomes proportional to a higher power of the energy. That is what's important to the number of microstates. If we want to calculate the number of microstates, we multiply the number of microstates for one energy split by the number of possible energy splits. So for 1 degree of freedom, that's just the value of omega 1, the number of microstates for one spring at energy E, multiplied by a point, the one energy distribution that is possible. As the energy in this system changes, the point doesn't change, so the number of microstates is constant for a one-spring system, no matter how much energy is in it. For 2 degrees of freedom, that's omega 1 multiplied by omega 2, the number of microstates for 2 springs at 1 energy distribution, multiplied by the line of possible energy distributions. As the energy in the system increases, the omega square stays the same, but the line increases. For 3 degrees of freedom, that's an omega cube, 1 for each spring, multiplied by the triangular energy split space. As the energy in this system increases, the omega cube stays the same, but the energy split triangle area increases. For 4 degrees of freedom, that's an omega tesseract, a 4D cube, multiplied by the tetrahedron in the energy split space. As the energy changes, the omega tesseract stays constant, but the energy split tetrahedron's volume increases. So you can see the gist, we just keep adding dimensions. So what this means is that as the number of degrees of freedom in a system increases, e.g. as the number of springs in the system increase, the number of possible microstates for that system grows at a rate of the energy to the power of the number of dimensions minus 1. To go back to Boltzmann's original thought experiment, there are way more than 5 degrees of freedom in the universe. So if we want to compare how the number of microstates grow with energy for the spring versus how the number of microstates grow with energy for the universe, we can assume the graph will look something like this. The original point we were making was this: how many microstates correlate to the different potential energy splits between the spring and the universe? We can find this out by taking the number of microstates for the spring with energy E spring and multiplying it by the number of microstates for the universe with energy E universe. When the universe has most of the energy, there is an astronomically large amount of microstates there and just a few in the spring, so the product of these values will be huge. And when the spring has more of the energy, there is way less microstates for the universe and the same amount of microstates for the spring. If we plug in some example numbers, we can see that there are a certain amount of microstates that correlate to the spring having most of the energy in the universe, but there are way more microstates that correlate to the spring having a tiny bit of the universe's energy. We can make 2 assumptions. 1, every microstate of the combined system is equally likely, and 2, the probability of observing a particular energy in the spring is proportional to how many microstates are compatible with that choice. So, if we plot how many compatible microstates against the spring's energy, we expect a curve that drops off very quickly, so we can base it off of the e to the minus x graph and swap out x for energy. We can now say that the probability of the spring having an energy E is proportional to this exponential equation. But to say that confidently, we will also throw in A as a constant next to the energy to make sure the graph scales correctly when mapped out against real probability. We don't need to know what A is yet, we can work it out later. Does this equation look familiar? It should, because it's almost the exact same equation we started with, the Boltzmann distribution. Pxp assigns probability to individual microstates, and Pe is the result of the groupings of those microstates by energy. The exponential is the same. The negative Hamiltonian in the first equation is equivalent to the negative energy in the second, and the constant alpha in the second equation turns out to be equal to 1 over kT in the first. So how did Boltzmann figure out that alpha equals 1 over kT? What we've done today is show how Boltzmann derived the Boltzmann distribution by assigning probabilities to energy levels through counting microstates. By applying this framework to real physical systems, Boltzmann was able to determine the value of that constant, and that's what we'll explore next. But on a deeper level, what we've done here is show the logic Boltzmann used to birth the field of statistical mechanics. Although it seems abstract now, we're just laying the foundations. We stopped treating the certainties we observe in the world as fundamental and started viewing them as the macroscopic emergence from a true fundamental microscopic collective. This is something that has some mind-boggling and far-reaching implications that we will explore in the next video, and it really lays the foundation for the quantum world. So thanks for watching, and I'll see you in the next video.